Picture the year 1206. You are standing inside a royal court in Diyarbakir, in what is now southeastern Turkey. A guest reaches for a wash basin, and a mechanical servant stationed in the corner begins to move. Its arm extends, water flows at a controlled rate, and it offers a towel once finished. Every motion is timed and repeatable, occurring on cue every single time. There are no strings here, no person hiding behind a curtain operating levers. This was the work of Ismail al-Jazari, a chief engineer who spent decades designing machines that functioned through pure mechanical cause and effect. These 13th century court novelties were an early blueprint for programmable robotics. Al-Jazari was applying a structured logic to machines long before the industrial age, yet his name remains largely unknown outside the history of engineering. The Islamic Golden Age is usually recognized for leaps in philosophy and mathematics. Al-Jazari applied that same systemic rigor to physical engineering. He solved tangible problems by cutting wood, casting metal, and balancing weights. Standard history textbooks often treat the centuries between the fall of Rome and the European Industrial Revolution as a technological void, jumping straight from ancient Roman aqueducts to Victorian steam power. The facts show a different timeline. The specific, verifiable mechanics Al-Jazari pioneered 800 years ago are the direct predecessors of the machines operating outside our windows right now. Take his court automata, like the robot waitress designed to pour drinks. Without electricity, Al-Jazari relied on fluid mechanics. He designed timed internal valves and weighted floats that allowed him to control the sequence of a machine's actions. This modern replica of the elephant clock shows how he applied these principles. Behind the elaborate shell of dragons and birds sits a functioning timekeeping device. Inside the elephant, a floating bowl slowly fills and sinks, pulling a trigger string. This releases a ball into a dragon's mouth, tipping a balance, and causing a figure to strike a symbol, marking the hour. The design was intended to symbolize the global origins of his engineering knowledge. The elephant represented India and Africa. The dragons represented Chinese mythology, and the phoenix stood for Persia. The elephant clock was an exemplary display of automated sequencing, demonstrating that complex instructions could be written using water flow, gravity, and balanced counterweights. Beyond clocks and royal novelties, Al-Jazari solved a major mechanical problem for heavy industry. He was the first to combine a crank and a connecting rod into a single, functional mechanical system. As this diagram shows, this combination allows you to convert continuous, circular rotational motion into a straight, back-and-forth linear path. He first applied this to a water-raising machine known as a sakia. By harnessing an animal to a horizontal gear system, the rotational pull was converted into the powerful linear pumping action needed to draw water from deep below ground. The crankshaft sitting inside a modern car engine uses this same principle in reverse. The engine uses the linear motion of the pistons to turn the shaft, converting that energy into the rotation that drives the wheels. He also refined the camshaft. By attaching shaped rotating cams to a single shaft, he could create controlled, repeating linear motions. This is how his automata performed their timed hand-washing routines. These kinetic mechanisms were the mechanical principles required to build the high-speed engines of the Industrial Revolution centuries later. These complex mechanical components survived the centuries because of his 1206 manuscript, the Book of Knowledge of Ingenious Mechanical Devices. Earlier engineering texts often relied on vague descriptions. Al-Jazari wrote a technical manual. He documented measurements, provided detailed schematics, and laid out step-by-step construction instructions. He included specific components designed for efficiency,